Hello, everybody. My name is Christopher Bias, and I am a senior at West Virginia State University. And I am graduating this spring, 2021, with my bachelor's in chemistry. Now, while this isn't my first time presenting for URDC, this is actually the third. This is my first time presenting for URDC from home, as I know all the other participants this year are dealing with the COVID-19 pandemic, but we're going to make do, and I'm still excited to tell you a little bit about my research. The title of my research is Organic Synthesis of Acylated Sucrose for Integrated Pest Management. I did this research under Dr. Michael Foltz at West Virginia State University, along with Megan Spilak, who was a high schooler at the time. She is now a college student pursuing her degree. So let's talk a little bit about the importance and the goals of this research, what we're trying to accomplish. The goal of this research was to synthesize a novel acyl sugar pesticide for use on tomatoes. Now, we all know tomatoes are a very crucial part of our diet, and they've been shown to increase HDL cholesterol levels. Tomatoes also boast a very high economic value. So let's talk about acylated glucose. The Solanum pinelii is a wild tomato species that exhibits very good insect resistance. This is due to its high densities of the type 4 glandular trichomes. And if you've ever noticed on a tomato, you look at the leaves on top of the tomato, they have these little hairs sticking out. What those hairs are these glandular trichomes you see pictured in the bottom right here. And these trichomes secrete substances that physically and chemically deter small pests, such as peach aphids and lacewings, pests that are detrimental to tomato crops. What you see here is the actual secretion of acyl sugars out of the end of the trichome. So here are some structures of those acyl sugar mixtures that are secreted by tomato trichomes. One of particular interest is the one on the top left here. So it's actually the shortest acyl chain. You can see they actually get kind of long. Let's talk about some previous research that was done on this topic. Mrs. Hannah Payne completed her master's thesis on synthesizing acylated glucose using a two-step protection of primary and anomeric alcohols, and an acylation step, and then two deprotection steps. So with that knowledge, we took that and applied it to sucrose. So you see we have a two-ring structure here. Same thing, the primary protection of the alcohols with TBDPS-Cl, acylation, and then the deprotection, converting the alcohols back to their original state. So let's talk about the first step here, the protection of the primary alcohols with TBDPS. TBDPS-Cl, you can see pictured here at the bottom. The TBDPS-Cl was added to a solution of sucrose, which is the starting material. Now, sucrose is just regular old table sugar. It was dissolved in pyridine and DMAP. DMAP acts as the catalyst. You can see DMAP, the structure of it in the bottom here. TBDPS stands for tert-butyl diphenylsilane, and DMAP is dimethylamidopyridine. So that was heated and stirred at 70 Celsius for 48 hours. And the crude product was then concentrated under reduced pressure on the rotovap and then purified via a silica gel column. So let's talk a little bit about a silica gel column. What we have here is a glass column that is packed with a wad of cotton, a layer of sand, a layer of silica gel, and then another layer of sand. Now what we do is we pour our crude product on top of that sand, and then with a solvent system, we can push that through the silica gel. And based on the polarities of the components in our crude product, we can separate that out. So impurities would come off either sooner or earlier than our desired product, and we would ideally get 100% pure product. But it doesn't always work out perfectly, but it's a pretty good method for purifying product. So the second step is an esterification of the remaining alcohols. The tri-protected sucrose, which was created in step 1, is dissolved in pyridine again, is then treated with isobutyryl chloride dissolved in acetonitrile. This is added via an addition funnel over the course of 45 minutes, And as it drips in, you can actually see it fuming, so it's a pretty cool reaction to watch. Reaction stirred at room temperature for 72 hours. The crude product, again, was concentrated under rotovap and purified via a silica gel column. So we are actually able to get a pretty high yield on this step. Now, the third step is a deep protection of the primary positions. The TBDPS groups here get cleaved in this step. The acylated sucrose, which is the product from step 2, is dissolved in THF in a plastic round bottom flask, and then it is treated with HF pyridine, which is added via a syringe over the course of 2 minutes. Reaction stirred at 25 Celsius for 72 hours. The crude product was then concentrated and again purified via silica gel chromatography. So let's talk about why a plastic round bottom has to be used for this reaction. Excuse me. HF will react, hydrofluoric acid will actually react with the borosilicate glass to form hexafluorosilicic acid and sodium fluoride and water. Now this reaction would, there's 2 reasons we have to use the plastic. Number 1, the reaction I previously mentioned would happen before our desired reaction ever had the chance to, because it's much more favored. And number 2, after 72 hours of stirring, we would no longer have a glass round bottom flask, because it would just completely dissolve and destroy the flask. So it's not every day you get to use a plastic reaction vessel, so this was pretty cool. So what does all this mean? What did we get from all this? Obviously, step 3 was incomplete, as indicated by the broken arrow on the reaction scheme. But we do have promising proton spectra for proton NMR spectra for the first 2 steps. That's the protection and the esterification. We were able to achieve very consistent yields on step 1, but low nonetheless, around 30%. Step 2 gave us a 85.4% yield, which is pretty high. So let's talk about what this all comes down to. We're about 2/3 of the way completed with this work. The exact structure of our products cannot be determined because we don't have a mass spec of it. NMR can only tell us so much, and we can only make good guesses at the degree of protection. So how many of those protecting group actually went on, and how many of those acyl groups actually are attached to the molecule. So a mass spec would be great for a clearer analysis of our product. Future work would definitely include completing step 3 and optimizing this synthetic pathway. So Megan, the student who was able to work with our lab through ACS Project Seed, got some really good hands-on lab practice. She was a high schooler at the time, keep in mind. So she got to develop a feel for a research setting, which is something very, very few high schoolers actually get to do. And she got some basic knowledge of advanced lab techniques. So things like, preparing a silica gel column, filtration. You actually see Megan preparing a TLC capillary spotter here using a glass pipette, which is heated up under a flame or over a flame and then stretched out to be a very fine capillary tube. She got to learn a little bit about organic chemistry and also create a strong network within higher education. So I'd like to thank the ACS Project Seed for allowing me to take Megan in and allowing me to be a mentor. It was very beneficial to me, and I know Megan feels the same way. I would also like to thank West Virginia Science and Research, HEPC, West Virginia State University Title III programs, and the College of Science and Math at West Virginia State University. And I'd also like to thank Dr. Foltz for letting me use his lab and being a very good mentor, along with all my lab mates you see listed here. They helped me every day and lended a hand when needed. So if you have any questions, I'd be more than happy to answer them at cbias4@wvstateu.edu. Just shoot me an email with any questions you have about this presentation or the research. And like I said, I'd be more than happy to answer. Thank you all for listening.